All right, let's look at your sample quiz. So the first thing that we have is they give us a graph and they ask us to identify absolute and relative maximums and minimums. Sometimes they'll use absolute or global. Those are the same terms, and sometimes they'll use relative and local. Those are the same terms. So in looking at our graph, if we are looking for the absolute maximum, it is the one absolute highest point on the graph. So that's going to be right here, and you can see that that's at -1, 2. Then for the absolute minimum, the one absolute lowest point on the graph, well, if you'll notice, this is going off to negative infinity. So there is no one lowest point on the graph. You can't walk up and put your finger on negative infinity and say, I'm equal to this value right here. All right, then our relative maximums and minimums, a couple of things. A relative maximum and minimum cannot occur at endpoints because the definition of a relative maximum is it's where your graph changes from increasing to decreasing, and a relative minimum is where we change from decreasing to increasing. That doesn't happen at an endpoint. Additionally, I don't know if this is the highest point relative to what's around it. Like the graph could keep coming up here. So absolutes can happen at an endpoint, but relatives cannot. So here's my relative maximum at -1, 2, and here's my relative minimum at 1, -1. All right, then for 2, finding our critical numbers, remember that your critical numbers are where your derivative equals 0 or your derivative doesn't exist. So first off, we're going to take the derivative. So we can say 4 times 1/4 x to the third, 3 times 1/3 x to the second, and then -2x plus 0. So here's our derivative. Let's set it equal to 0. So we're going to factor this. The first step in factoring is always take out your greatest common factor, and then this quadratic will factor as well. So once I get it factored, I'm going to set each one of my factors equal to 0, and that gives me my 3 critical numbers of 0, -2, and 1. So critical numbers are where the derivative does not exist as well. And so if we look at this derivative, is there anywhere that doesn't exist? Well, no, we're just looking for things that wouldn't be in the domain. Like I can't have 0 in the denominator or a negative under an even indexed radical, but I don't even have a fraction or a radical. So this is a polynomial. It's well behaved everywhere. So there won't be any other critical numbers except for those 3. All right, then for B, we have a fraction. Now, I would always want to look to see, is there any way to simplify this first before I just jump in with low D high minus high D low, but there is no way to simplify. So we're going to say denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So simplify that a little bit. X times 2x is 2x squared. -1 times 2x is -2x. And then 1 times the x squared plus 3 would be 1. When we distribute this negative right here, it changes every sign that comes after it. So that's why it's -x squared and -3. So 2x squared minus 1x squared gave us 1x squared, and then minus the 2x and minus the 3. So again, a critical number is where your derivative equals 0 or where your derivative doesn't exist. So let's start with where the derivative equals 0. The only way a fraction equals 0 is if its numerator equals 0. So we're going to set the numerator equal to 0 to figure out where our derivative equals 0. So again, this will factor, and then we can set each of those factors equal to 0. Then we want to think about where the derivative doesn't exist. Where the derivative doesn't exist is where I have a domain issue, like I can't have 0 in the denominator. So I'm going to set my denominator equal to 0 to see where this doesn't exist, and that would be at +1. So those would be my critical numbers of 3, -1, and +1. All right, then for C, we had a trig function. So we had 2 cosine x plus x. So the derivative of cosine is going to be negative sign, so we'll have -2 sine x. Derivative of x is 1. So again, we're going to set the derivative equal to 0. So I'll subtract 1 from both sides and then divide by that -2. And I've got sine is equal to 1/2. So you can either draw out the whole unit circle if you want to, or you can just draw your first quadrant to see where your sign value is going to be equal to 1/2, and that's going to be right here at pi over 6. And then we know sign is positive in the first quadrant and the second quadrant, so I'm going to give the second quadrant pi over 6, which is 5 pi over 6. Then the second thing I need to think about is where the derivative doesn't exist. And if you think about it, no fractions or radicals here. Trig functions are well behaved within their domain. They're continuous within their domain. And the only domain problems would be fractions or radicals, and I don't have those. All right, so then for 3, they ask us to find the absolute maximum and minimum on the interval, and we're using the same thing that we just had in 2b and in 2c so that we can use that work that we already had. So this is that same work that we just talked through a second ago to get these critical numbers. All right, so when you're trying to find the absolute maximum or minimum on an interval, it can occur at your critical numbers or it can occur at an endpoint. So I'm going to need to check each of the critical numbers, and I'm going to need to check each of the endpoints. So I'm going to take -1 and I'm plugging it in, and it's the absolute maximum or minimum of the original function. So when I take -1, I'm plugging it into the original function. So -1 squared would be 1 plus 3 would be 4. -1 minus 1 would be -2. So 4 divided by -2 would be -2. If I plug in 1, you can see in the denominator, I'm going to get 1 minus 1 or 0. 0 in the denominator is undefined. Then I'm going to plug in 3. So 3 squared is 9 plus 3 is 12. And 3 minus 1 is 2. So 12 divided by 2 is where we're getting this 6. Then we'll plug in -2. So -2 squared is 4 plus 3 is 7. -2 minus 1 is -3. So there's 7 over -3. And then plug in 5. 5 squared is 25 plus 3 is 28. 5 minus 1 is 4, so 28 over 4 would give us 7. So out of -2, +6, -7/3, and +7, we're looking for the absolute highest point and the absolute lowest point. So the absolute highest value is 7, so my absolute maximum is 5, 7, and the lowest point is this -7/3. So the absolute minimum is -2, -7/3. All right, look at the next one. So again, we're going to do the same thing. We've already got our critical numbers from the work that we had done previously. So we're going to check those critical numbers and those endpoints. So you can see we're going to plug in pi over 6, 5 pi over 6. And then here's our interval up here. We're going to plug in the 0 and the pi. So when we start off with, the function was 2 cosine x plus x. So we've got 2 cosine pi over 6 plus pi over 6. So cosine at pi over 6 is square root of 3 over 2. So again, you can see that right here. So we'll have 2 times square root of 3 over 2, which is just square root of 3. So square root of 3 plus pi over 6. And if you want a decimal approximation for that, that's 2.26. All right, then we're going to plug in 5 pi over 6. So 2 cosine 5 pi over 6 plus 5 pi over 6. So cosine at 5 pi over 6 is going to be the same value, square root of 3 over 2, but cosine in the second quadrant is negative. So it would be negative square root of 3 over 2 plus 5 pi over 6. So the 2's would drop out, and we would have negative square root of 3 plus 5 pi over 6. And again, a decimal approximation for that would be 0.89. All right, now let's check our endpoint. So we're going to plug in 0. So 2 cosine 0 plus 0. Cosine at 0 is 1, so that'd be 2 times 1. So 2 plus 0 gave us 2. And then if we plug in pi, 2 cosine pi plus pi, the cosine at pi is -1. So that'd be 2 times -1 plus pi. So -2 plus 3.14 gives us 1.14. So again, we're looking for the absolute highest. So you can see 2.26 is the absolute highest. So that's going to be my maximum, and that occurred at pi over 6. So pi over 6 square root of 3 plus pi over 6, that would be my absolute maximum. And then 0.89 is my lowest value. That's my absolute minimum. So that would be 5 pi over 6, and then negative square root of 3 plus 5 pi over 6 for my absolute minimum. Now, something to note is that over here, both my absolute maximum and absolute minimum came from the critical numbers, whereas over here, both of them came from the endpoint. And you can have one of each kind of thing. So that's why it's important that we check both of those to find absolute maximums and minimums. All right, then some true or false things. So number 4, all critical numbers are local maximums and minimums. That's false because All of your local maximums and minimums have to come from critical numbers. But just because it's a critical number doesn't mean it's going to be a maximum or minimum. You still have to test it. That's where the first and second derivative tests come in. So the first one is false, but the second one is true. All right, then endpoints can be absolute maximums and minimums. And then the next one, endpoints can be local maximums and minimums. Yes, endpoints can be the absolute highest point or the absolute lowest point, but remember the definition of a local maximum is that's where we change from increasing to decreasing, and that doesn't happen at an endpoint. Additionally, I don't know what's going on in that locale, so I can't say it's the highest value in that locale. All right, then 8, every continuous function on a closed interval will have both an absolute maximum and minimum. That's exactly what we were just working with. So if you have a closed interval, if nothing else, the absolute maximum and minimum will occur at the endpoints. So yes, you will have an absolute maximum and minimum with every continuous function as long as it's on a closed interval. All right, then the next one, if the first derivative is positive, then the original function is increasing. That's true. And where it's negative, it's decreasing. Then 10, if the derivative changes from positive to negative at a critical number c, then the function has a local minimum at c. It's actually a local maximum, right? When it changes from positive to negative, that's changing from increasing to decreasing. So that would be a maximum, not a minimum. If it changes from negative to positive, from decreasing to increasing, that would be a minimum. All right, and then the last one, if the first derivative is increasing, then the original function is concave up. That's true, because if the first derivative is increasing, that's where the second derivative is positive, and where the second derivative is positive, it's concave up. If the second derivative was decreasing, that would be where the second derivative was negative, and that would be where the original function is concave down. All right, then for number 12, we want to find all of these things that we've been working with. So for the first couple of things, increasing, decreasing, maximums, and minimums, that's all going to come from the first derivative test. So first off, I need to identify my critical numbers. So I'm going to take my derivative and set it equal to 0. So derivative of x is 1, derivative of x squared is 2x, derivative of negative x cubed is negative 3x squared. So I'm going to set that whole thing equal to 0. I personally just don't like to factor when my leading coefficient is negative, so that's the only reason I factored out a negative 1 right here. You wouldn't have to. But then what we've got left is easy to factor. I'm going to set each one of those factors equal to 0, and there are my critical numbers. Also, critical numbers are where the derivative doesn't exist, but there is nowhere this derivative doesn't exist, so these are my only critical numbers. So let's make a sign graph for the first derivative, so you can see it's labeled here. So there are my x-intercept, my critical numbers at negative 1/3 and positive 1. So I'm going to pick a test point. I like to use 0. I can't use a value that's already a critical number, so 0 is good. So I'm going to take 0 and I'm going to plug it into the derivative, not the original function, because I'm making a sign graph for the derivative, right? So when I plug in 0 into this derivative right here, I get a positive 1. So if it's positive at 0, cross a single root, the sign changes, cross a single root, the sign changes. So there's my sign graph. So anywhere my first derivative is negative, my original function is decreasing. Anywhere my first derivative is positive, my original function is increasing. Anywhere my first derivative is negative, my original function is decreasing. So additionally, where my graph changes from decreasing to increasing, I'll have a minimum. And where my graph changes from increasing to decreasing, I'll have a maximum. So that's how we got our intervals of increasing and decreasing. And that's also where we got our maximum and minimum. So here was our minimum at negative 1/3, and here was our maximum at positive 1. Now, those are maximums and minimums of the original function. So I'm going to plug those back into the original to get the y value that goes along with them, and that's what we've done right here. We're going to do almost the exact same thing for the second derivative to determine our concavity and points of inflection. So we're going to take the second derivative, set it equal to 0, and that's going to give us our possible point of inflection. So let's make a second derivative sign graph here. So here's my only potential point of inflection. I'm going to pick a test point. I'm going to use 0, and again, I'm making a sign graph for the second derivative. So I plug that into the second derivative, and I get a positive value. So it's positive here, cross a single root, the sign changes to negative. So anywhere the second derivative is positive, I'm concave up, and where it's negative, I'm concave down. Where we change from concave up to concave down, I have a point of inflection. And that's a point of inflection on the original function, so I plug it back into the original function to get that y value. And so those are my solutions.